Okay, welcome back class. Last time we discussed the three types of noises. So it was the impulse noise, which were like white dots on the image. Then there was another salt and pepper noise, which were black and white dots. And then the third one was the Gaussian noise, which is a small random value which is added to the original value of the pixel. So for example, if the original value of the pixels in some surrounding area is 60 or 61 or 62 or 63, the noise will make it either 70 or either 50. So it will add plus 10 or minus 10, just a rough idea. So we also discussed that we need to remove this noise from the images. So to remove this noise, what we need to do is we try, for example, to take the average. So for example, let's say there is a pixel over here, its value is 50, and the surrounding pixels are less value, 35, 34, and maybe this is 29, and the below is 31. So just to give an idea that these pixels over here in the surrounding, they show a little value, whereas this one in the center, it is much higher value. So one method to remove noise is that we take the average of all the pixels in the surrounding. So we take the average of all these pixels. So for example, there is 35, there is 29, there is 34, and there is 31. We take the average, and also we put the original one, which is 50. We put them all, add them, whatever it is, the answer. For example, here it is 19, and then there is 3, 6, 9, 10, 15, and 17. So this 17 value we then divide it by 5, average. Make an average, because there were 5 values we added, so divide by 5. So this will give us an average value. So it will give us, for example, 5, 3 is 15, and 5 is 25, and then 35.8, which we can say almost 36. So this just gives you an idea that I removed this value of 50 with an average value which is 36, which is much closer to the neighbors. So whenever we have a lot of values, we can take an average to make the noisy value a little down, or if it is too low, it will become up. So if it is, for example, 50, it becomes in this case 36. But let's say it was very less, it was 15, then it will become much higher. Maybe it will come close to 30, 29. So this is how the noise is removed. But the important thing is that to remove the noise, what we do is, let's try to understand it with the help of example on a signal. So remember, we discussed last class that whatever concepts we discuss over here in computer vision, we will try to practice them on the signal processing. So in the signal processing, let's say you have these signals over here. This is the time axis. These are the signals values I sample over the time. Some of the values, for example, they are noisy. So noise in signals comes for many reasons. When we communicate signal, noise can be added, or when we want to store it somewhere, noise can be added from some source. So these are the noise values over here, and we don't know, maybe the other ones are also noise, maybe the very low values are also because of noise. Noise, what is it? It's something that is different from the normal pattern. So how we can remove the noise? What we want to do is that take this original and convert it into something which is more smooth. So smooth means it is not rough, not too much up, not too much down. So what we want to do is we want to replace each pixel with an average of all the values in its neighborhood. So we normally call it a moving average because we try to take an average based on the neighbors, and this average we keep on moving. So for example, here I take the average of 5 values, 1 2 3 4 5, and the value is then put over here for this. Similarly, if I want to take an average for this, I will select 2 pixels on the left, 2 on the right, and then I will put the average over here in the center. Why I select 2 on the left, 2 on the right? It depends on the size of the window. We normally call this thing as window. We call it a moving average because this window, it is moving when we are changing to the next pixel. So it moves from the starting point till the end. So this is a first attempt of our solution. This is what we want to do. This is the first attempt, just to give you an idea on the signals. So, but there are two main assumptions. So this is important exam question also. Two main assumptions, two main things I suppose. Two main things must be there already. One thing is that, so assumptions, they come over here. One thing is that the true value of the pixels are similar to the true value of the pixels nearby. So when I gave you the example 50, and then there is 35, there is 34, and there is 29 and 31, we said that all the pixels, we suppose that their values are in the similar range. So they are almost in 30s, between 30 and 35. That's why we said that this center value, it's noise. It's not good. Okay. So one thing is that the pixels in the nearby, they all have almost same values. For some place where the pixel value changes a lot in some image, we can't detect the noise easily. And the second thing is that noise, when it is done, it is added independently. It does not depend on the past noise. So for example, noise over here was added, so almost a noise of 15 values. So it was added, it becomes 50. Now if there is a noise somewhere else in the picture, it will also be in the same range. Maybe it adds 15 or 10. It is not possible that the noise somewhere adds based on the previous value. It adds with 50. So it is not possible that it will add 50 plus 15, which is 65. That's wrong. That's the meaning of the second thing. The noise is added independently in each pixel. It does not depend on any other past value or in the surrounding pixels. These are the two important assumptions. So this was a quiz we discussed last time. If the noise is added to a function, if noise is just like any function which is added to an image, we can remove this noise by subtracting. So remember, if you remember that we discussed previously, I is an image, then noise is represented by this symbol, and this gives us the I prime or a modified image. So you see, noise is added to the image, so it's an add operation. So is it possible that I can subtract the noise? So if I subtract n, it will cancel, then I remains over there. So can we subtract the noise from the image? Just pause over it, think over it, because it's a reversible process. We know how to do subtraction. We know how to subtract signals. So the answer for this thing is that we can subtract, but the problem is we actually don't know what is the noise. What is the noise function? What is the exact value of noise? We cannot reproduce this noise that is over there. It's not possible to reproduce the noise. For example, noise for one pixel, it is 15. It does not add 15 everywhere. It adds 15 for one random pixel. We don't know which pixel it is. So we cannot subtract 15 because we don't know which pixel was it that got the extra value. So that's the problem. So we can the addition of noise is a reversible thing, but we don't know the noise function. So we can't actually do the subtraction because we don't know where it occurs. So if I have an image like this, these are the image pixels. I don't know which one of them, either this one or this one, which one of them is damaged or destroyed or modified by the noise. That's the problem. I hope it's clear. So here is an example of the weighted moving average, where what we do is that we take the surroundings, we take the average of a small window area. Okay. So the previous approach that we saw was the simple moving average. This one, it's simple moving average. Moving average, and this thing over here is the same. This is also simple moving average. In the simple moving average, what happens is that all the neighbors, they have the same value. Okay. For example, I want to make the find the noise in this component, in this one. So I will take two neighbors from the left side, two from the right side, and one is itself in the middle. So 5 values, and I divide by 5. So what we do is that I have 5 values, I divide it by 5, I add the values, and then I divide by 5. The result is that the values, they change. All of them, they go higher. You see over here, for example, because of this noisy component, this correct value also goes high. You see over here, all of them have gone higher. Why they have gone higher? Because of this noise. This noise has now been scattered across multiple pixels, multiple values. I don't want this thing. Why I don't want this thing? Because remember, this noisy pixel, I don't want that it affects other pixels that are far away from it. For example, this noisy pixel is far from this pixel by 2 positions. So 2 positions far. So I don't want it to affect my place like this. So for this purpose, what we can do is that this is the simple moving average. I can introduce the weighted moving average. So look at the concept. The concept over here is that whatever is the value over here in the center, multiply it by 6. Because this is the original value, original pixel. I want to have more effect of this value on my answer. And the surrounding ones, these two values, they have little effect, so I multiply by 4. And the ones that are even more far away, I want them to have less effect on this value. So this noisy pixel, which is very high, I don't want this to have too much effect on the middle value. So that's why we multiply it by 1. So this is called as weighted, non-uniform weighted moving average, or weighted moving average. So overall, this thing is called weighted moving average. So we take a window, we call it moving average because the window is moving over the whole area. And the weighted moving average is the one where the pixels that I consider, their weight is not same. Some pixels are more important, the one in the middle, and the ones that are away from the middle, they have less importance. So for example, the pixels far away, they have the least value of 1. The multiplication factor is 1. How it will work? So let me give you the idea. Let's say the middle pixel value, it is 31. and the one that is on the left is 32, and the other one is, let's say, 20, 30 or 29, 29. And on the right side of 31 there is another pixel that is also 31, and the noisy pixel is now 50, 55 maybe. Okay, now what we want to do is that what is the purpose of this weighted moving average? The purpose of this weighted moving average is that the 55 should not have too much effect on 31, less effect. I don't want that 31 is disturbed. 31 is a correct value, whereas 55 is noisy pixel. So what we do is that to take the average that we want to calculate, remember we want to make the 55 correct, but that will come later. For now, we don't want 55 to affect the 31. So what we do is we multiply 31 by 6, and 32 and 31, the other ones, by 4, and the outermost values by 1. Now you see 55 is far away, so it has less importance. So this will come out as 186, and here it will be 124 and 128, and the last ones will be 29 and 55. So now you see this is the actual effect they will have. Because the center value is more important to me, it has more weight, so it is 186, much higher than the other values. And the outermost are less important, that's why they are multiplied by 1 only. So that's why they are 55 and 29 only. So this is weighted moving average. We put a weight or a value to each of the neighboring pixels. The one that are more close, they have more weight. The one that are far away, they have less weight. So what we do next is then we add them. So these are the values. I add them. I add all of them. And then because I added them with different weights, now I will divide the whole sum. I don't know, I haven't calculated. Let's say the sum is some value like 430. And I divide it by what? Should I divide it by 5? No. If you divide it by 5, it will be a wrong answer. Why? If you divide it by 5, it will give me some answer around 90. So 90 is correct? No. The whole range of values was 29, 32, 31, 31, 55. The correct value should be in 30s. So it is not correct, this one. Why it is not correct? Because I added them by first multiplying, so I will divide it by these weights, the sum of these weights. So it is 6 and 4, 10, it is 14, 15, 16. So it should be divided by 16. So it will give me same value in the range of 30s, somewhere in 30s. So I hope it is clear. This is called as weighted average, whereas the previous approach where all the neighbors have same value, we call it simple moving average. So weighted moving average is not this one, remember. This one is not weighted moving average. This was to explain you. Weighted comes next. This one is the simple one, which is simple moving average or uniform moving average. Another word used is uniform moving average. So here you should write uniform. I should change this slide. This is not correct. It is uniform moving average. Uniform means same. So this was uniform moving average, and the other one, this one, is weighted moving average because the weights are different. So this is now the concept we learned for signal processing. This is what we did now. Now what is the effect? You see this signal is very high, but it could not affect the original signal too much. Original signal, you see, it still affects, but effect is much less. So you see the values are now much smooth, going up like this. And if you go back, see the original, it was disrupted over here. The value was not correct. Suddenly go up. That's not good. Clear? So this is the problem. Here we see this. And why one question is that when we are making the moving average computation, why we choose the weights? Why should we choose? How should we choose them? Odd or even? Why? What's the reason? So the answer for this is that we choose the weights normally as odd. Why we choose odd? For example, odd weights, they can make symmetry very easily. This is the pixel. I want to make an average for this value. So I choose maybe one value on both the sides. So total will be 3. Or in another scenario, which was what we saw over here in our example, I have 2 values on the left, 2 on the right. It is 5. Another scenario, I can have 3 values on left or 3 values on right. It will be 7. So it will be always an odd. So odd makes it easy to have a middle pixel value. So the even, we don't use it, and we don't select any of them. It's always odd that we use for the moving average. Now you have seen the concepts on the signals. Now we will come back to the image processing. Remember, we discussed in last classes that we will try to implement concepts on the signals, and then we will implement same concepts on the images. That is why this course on computer vision and also image processing, they are very closely related to signals and systems courses. So how we do this moving average, making a window on the images? In the case of images, what we do is that we make a window like this. Remember, the signals are one dimensional, so we make window over there which is one dimensional window like this. For example, the window size is 5. I want to make an average for the middle value, so I select 2 on the left and 2 on the right. But images, they have 2 dimensions. They have X and Y. So in this case, the window will also be a 2-dimensional window. So here the window is a 3 by 3 matrix. 3 by 3. So what I want to do is that I consider over here, just take an example for now. This is a window I make, which is a 3 by 3. I select all the pixels in this range. And what I do is that I take the average of these pixels. So let's say we have an image over here. Now you see this image. Okay. What you see in this image? All the values are 0 on the surroundings. In the center there is a big, you can say, white space. So pixel value is around 90. So it's a white dot, you can say. And there is noise in this image. Where is the noise? One noise is over here. There is a 0 in the middle of all the 90s. That's a noise. And there is one more noise which is basically 90 value in the middle of all zeros. So these are the 2 noise values. So we want to see what will happen by our averaging technique that we learned on the signals. So when I take the average of this window over here, 3 by 3 window, the average for this value is 0 because all of them are 0. Okay. Next, I move the window. That's why the name comes, moving average window. So moving average. So basically the window is moving. So window was there. Now it has moved by 1 pixel to the left. So remember, the window starts with some width over here. The width is the 3 rows. And we keep on moving every time. So we keep on moving 1 pixel at a time to the left side, to the columns on the right side, right side. So when we moved over here now, so you see over here in this window now, 3 by 3 window, there is one value of 90. So if you have 9 overall values, 8 of them are 0, 1 of them is 90. So overall, I will have lots of zeros. plus 90. I will divide it by what? I will divide it by the number of pixels, so that is 9, because we are using now the uniform moving average. All weights are same. So it will be 90 over 9, it will give me 10. That's why we see the 10 over here. I move next, window moves. Now there are 290 values. So if you calculate it, you will see it is 220, the average. I keep on moving. Now there are 390s. So it is 30. Again 30. And this is it, the whole. If you apply this overall, now you will see what happened by the averaging technique. That what averaging technique did is that the 90 values that were over there, they have caused an effect. So 90 values, if you look over here, they started over here. Okay. So these 90 values, yeah, they started here. 1, 2, 3, yeah. So these 90 values, they have the ones that were on the corner, they have spilled, they have scattered over there in these areas. So the 90, it has passed its value a little bit, 20 and 10 in the surroundings. So the surrounding becomes more, gets more value. Whereas the 90 retains over here. Important point I wanted to mention over here is that the pixel number 5 in this row, the pixel number 5 in this row is now a bright value. It is no more a noise. Similarly, the other pixel value is also no more a noise. It was a 90, now it is 10. So both the noise values are gone, totally gone. That's a very good achievement. But there is a drawback, there is a bad point, that before there was no value over here, now there are little bit of values. Okay. So you can just take the idea as if sometimes small children, they are playing in the park and they make a small mountain out of sand. Okay. And if you want to remove that small mountain or mound of sand, what you can do is that you take that sand and you scatter it on the whole area. So the mound or the mountain is gone, but that sand now has been added to the whole place a little bit. Little bit sand has added in the whole of the surrounding areas. Clear? So that's what has happened over here. I hope this concept is clear, but the important achievement we did is that noise is gone. So the formulas are not interesting for us. We normally don't take formulas over here for this course, so you can ignore. You don't need to remember it. So the concept that we explained over here, the moving average, this concept is the one that in signal processing we normally called as correlation. So if you remember, in signal processing courses, there was a concept of correlation of signals. So correlation is basically like this, where you take one signal and move it over another signal. So it is called correlation or cross correlation. So if you have two signals, for example, F is your image and H is your small window. This is your window signal. In this case, in the previous case, it was the 3x3 window. Remember, image will be very large. Image can be, for example, 1000 pixels multiplied by 800 pixels. Just an example. Okay. So images, they can be large, they can be different, but a window will be same, and normally it's very, very small. In this case, our case, it was 3x3 window. So the operation that we did over there, this whole operation, remember the window that we started, it was started and it was moving in this direction, When this row completes, okay, it will move 1 pixel down. So next time it will start here, next row, and it will go on in this direction. So it will keep on doing for all the pixels. And one interesting thing you should remember is that when the whole operation is finished, the 1 pixel will be wasted in the outside. That we will see in the future, that discussion. 1 pixel in the whole brown, in the whole surroundings, in the whole of the border, it will be wasted. So this is what we saw. This operation overall is same as just you imagine that, for example, I write something in the class on the whiteboard, and then if I want to erase the whiteboard, what should I do? I will take the eraser and I will move it over the board. So eraser is small, but I am using it over the whole area slowly. So that is the same concept over here that is applied. The window is applied over the whole image little by little. So this operation that we move the small window over the whole area, this is the correlation operation for images. We call it cross correlation or correlation, and there is a special symbol for this. It is this symbol, a cross inside the circle. This is the correlation symbol. Clear? This small window that we use, this window is normally called as mask or kernel. And overall, this process that we do, the process of correlation, we use the small one over here, the small mask or the kernel, we apply it on the image. We overall call it filtering. That is one the name of the chapter also, the filtering. So this is how we apply the mask or the kernel on the images to achieve something. This concept is very important because it will be repeated many times in the future examples. Okay, we will be using kernels for many different uses. We will be using it for changing the shape of the image. We will be using it to find to take the derivative of the image. We will see what does it mean. We will see it in detail. Clear? So the weights and the shape of the kernel are called as, what should be the size of the kernel? For example, we saw over there the kernel or the window. How much weight should be used and what should be the size? For example, the size over there used is 3 by 3. Okay, and because each value of the kernel, each value is considered same, that's why the value inside the kernel for every pixel is 1. In the future we will see different cases. Here it was 1, all of them. So it was a uniform moving average example. So these weights that I use in the kernel and the shape of the kernel, it is 3 by 3 or it can be 5 by 5 or even more bigger. What we call them? For the filter we call them coefficients. So coefficients is correct answer, others are wrong. It's not a mask. Mask is itself the kernel. Filter is also called as mask or kernel. The values, the weights and the shape of the filter or the mask or kernel, they are called as coefficients. Clear? So what makes a good kernel or a filter? We have seen this example. This is the example of a kernel which is uniform weight kernel. All the weights are same. Remember, you must divide by 9, the average, to make it an average. Okay. One simple solution I will give you. Keep this rule in your mind. Always keep it in your mind that the overall value of the kernel should not change. Okay, it should always be equal to 1. Okay, so over here you see the values 1. How many ones are there? So there are 9 ones. So if you add them up and divide by 9, it will be 9 over 9, it will be equal to 1. So basically this kernel, when you are applying this kernel on the image, basically you are multiplying it with 1. And you are basically not changing the image. You are not modifying the image. That is the important principle of filtering. The purpose of filtering is just to take an average. Just the pixel values, for example here it is 0, try to readjust them from the surroundings, take the value, don't add any new value from outside. Remember in media computation course you must have you have seen over there, you must remember that if I multiply a pixel value with some outside value, the pixel intensity will increase. For example, if I multiply it by 2, what will happen? The value 90 will become 180, which means the pixel intensity will increase. And remember over here, our purpose is not to modify the image. That's not allowed. I don't want to change the image. I just want to make an average of the pixels to remove the noise. Similarly, if I am multiplying the image with a smaller value, for example less than 1, in that case the image intensity, the pixel value will decrease. If it is 90, it will become 45. Means the pixel will become more dark. So these are not allowed. 2 is not allowed, 0.5 is not allowed. That's why remember the rule, the mask or the kernel should have the same value, which is 1. So if I have 1 1 1 inside 9 times, then I will divide it by 9. Because all the values in the filter are same, that's why we call it uniform filter, or we also call it box filter. Clear? It is also called as box filter. So here is an example. Now this is the example on the real image. How it works on the real image. You see over here, there is an image. Okay. When I apply the filtering, the box filter on this image, what happens is that it will change the values. One effect of filtering is that filtering will smooth the image. It will remove all the noises. All black dots, all white dots, it will remove it. But one side effect of filtering or averaging is that the image will become blur. Why it becomes blur? Because it tries to take the value of the pixel and it tries to make it average, more close to its neighbors. So when all the values are becoming more like their neighbors, the image becomes blur. It is not so sharp. Sharp image occurs because the value is high at some place. For example, this white place, it is maybe very high, 90. When I take the average, all the values become little less over there. So in this surrounding, all the values, they will become, for example, 70. Whereas the dark spots, they become more high. So original value, the original image, when we make it, when we remove the noise, it becomes blur. That is the must result of box filtering. So exam question can be box averaging or box filtering. It will remove the noise. What is the side effect? It will blur the image. It will smooth the image and blur it. Blur image is also smooth, remember. So drawbacks of filtering, averaging filter are, remember, we are using the averaging filter, all the values of the kernel are same. So what happens is that it will make the image more blur. It does not remove the noise perfectly. Same drawback as you saw previously. Go back. Remember what was the drawback of this approach? Uniform averaging, moving average. The drawback was that it does not remove the noise completely. Same is over here for the image. When we say that uniform averaging, what is the drawback? The drawback of averaging filter, it is basically averaging filter is same as uniform average. Uniform average filter, the drawbacks is that it do not remove the noise completely. The squares that it produce, they are not so smooth. So filtering an image with a filter that is not so smooth, it will be long. We are trying to blur the image, but we don't remove the noise perfectly. So what we do is that to remove this drawback, we use another filter where the center value is more higher. For example, in the center it is 15, and the surroundings it is maybe, or maybe it is center it is 6, in the surrounding is 4, and then even in the outside far away it is very less. So do you remember anything from this? It is the same weighted moving average filter we created for a single for a signal. So it is basically the same thing we make over here for a 2D image. So if you see, this is basically, if you represent this as an image, it will be like a blur spot. It will be like a bright spot. In the center it is more bright, outside it is less bright. As you go out, the brightness becomes lesser. And if you take the 3D of this thing, it will be like a mountain. So you see over here a mountain, there is a peak, and on all the sides it is going down, and it is a smooth mountain from all the sides. Clear? So when you want to blur the image perfectly, you will try to use something. So the quiz over here is to blur a single pixel into a blurry spot. So you want 1 pixel, for example, to take an average. We would need to filter the spot with 3 by 3 uniform weight. Uniform weight means that all of them are 1, or 11 by 11 square of uniform weights, or something that looks like a blurry spot, higher value in the middle and lower values on the edges. Now they want to ask you that if you want to make an average, if you have an image, you want to remove noise from this image, noise removal by making the image, by taking the average, image will become a little bit blur. We don't want to make too much blur. Okay, we want to remove noise but with less blur. One method is you use a 3 by 3 matrix, 3 by 3 kernel. Okay, if you use the 3 by 3 kernel, it will make blur, some blur, and noise remains over there. Okay, if you increase the size of the kernel 11 by 11, more blur will be there. Noise is removed, but there is more and more blur, because when you increase the size of the window, you are taking more average on a bigger area. 11 by 11 means that on a single, if you remember the signal processing example, it will be a window which is size of 11, 3, 6, 9, 10, 11. The window size is 11. So you want to take an average for this pixel. You take 5 on the left and 5 on the right. So definitely if there are more pixels from the surroundings that you average, they will have more effect, and this value will be more disturbed. So when the when the window size is larger, the blur will be more and noise is reduced also. As compared to the first one, the second one will be more blur and less noise. But the third one is the best approach. Why? Because as compared to those uniform weights, the weighted average is better because it will not make the image too much blur but reduce noise. So it will be less blur as compared to those and less noise. Clear? So this is it. This is what we wanted to discuss over here. So the correct answer is the last one. So remember, this kernel that you see over here, this kernel, this one is much preferred, and this kernel is basically called as weighted average, or we also call it Gaussian kernel. There was a Gaussian noise. Gaussian noise means that the value is added based on the pixel. Pixel value is 60. Noise will be plus 5 or minus 5 depending on the pixel value. The original value in the surrounding is 60s, so the noisy pixels will be either 65 or 55. Same is the case in the Gaussian kernel. It is a peak value in the center and surroundings are slowly decreasing. So here is the Gaussian filter now. This is the example of Gaussian filter. In the case of Gaussian filter, the center pixel, that is one we want to average. It will have the more weight and the surroundings will have less weight. So here it is 4 and the surroundings is 2, 2. So how it works is that when I apply this filter on the noise, now it will have more effect. It will change the pixels. So nearest neighboring pixels will have more influence in this case. So it will remove the noise more efficiently. So why we call it Gaussian noise? Why we call it, sorry, the Gaussian filter? Because the shape that it produces, it is same as the Gaussian function in mathematics. The Gaussian function in mathematics is represented by this shape, which is same as this kernel. Gaussian 3D is like this, but if you try to take the kernel as an image, remember kernel is also an image, so it will give you some image like this. Center is very bright, whereas the surroundings are becoming less bright. Here is the example. When you do the smoothing with the Gaussian, what it will do is that it will do the blurring, but it will make the blurring more smooth and it will remove the noise. In this case there is no noise, so you don't know, but we will do in the lab practical on removing the noise. So you see, this is the smoothing with the Gaussian, this is smoothing without Gaussian. Now take these two images and repeat them quickly, front, forward, back. You will see the difference. The one with the Gaussian, this one, it is more smoother. Okay, so it is blur, but it is smooth. Whereas this is blur, but if you look carefully, there are lines that you will feel over here. There will be lines, patterns. We don't want these patterns. These patterns are occurring because of bad filtering by the uniform filter. Look carefully these two. You see these patterns? They are clear. The one in the red box, they are clear patterns. So these patterns, they occur because of uniform filters. So two filters we have studied today: uniform filters and Gaussian filters. Gaussian are much better. Leave these equations. I will not ask any question regarding the equations. So how much we have seen the Gaussian? What about its shape and size? Gaussians we showed till now they are isotropic. The isotropic is another word for circular. Remember, they are like a mountain, a round mountain. Okay. So in terms of computers, when we discuss the filters, we normally talk about the size of the filter. Either it is 3 by 3 window or size, or 5 by 5 and 11 by 11. I hope you are clear now that always the size of the filter is in odd. Why it is in odd? Because we want the average for the center value. So for the center, all the sides from the center, they are of same length, same distance. So here is a discussion on the sigma value. We don't discuss sigma, so leave it. But there can be very different types of, just to give you an idea, the Gaussian can be of different shapes, different types of mountains. So don't worry, we will not discuss. Here is the effect of sigma. We don't discuss this also. The code given over here is MATLAB. We will be using Python in our labs, so you just ignore all this. So this quiz is also related to sigma, so leave it. This is also again related to sigma. So all the slides related to sigma, just cross them. Cross. So this is it. This is your chapter number 2. This was the last part for this chapter. In this chapter, to summarize, in this chapter we studied the filtering, the idea, the concept of filtering. Basically, the topics we covered in this chapter, they are related to image processing. You should know these things from your image processing course, but I revised to make all the class at the same level. This is not computer vision. Computer vision will be based on these things. It will come in the future. Clear? So this is what we studied over here. We saw two types of filters, the uniform filter and the Gaussian filter, and what effect they make on the images and how we filter. First we saw the example on the signals, and then we saw the example on the images. After this we will go to the lab side and we will do the practical for these in the lab work. So see you then over there.